So that average is not just a straight average, it's based on how many of each of them there are, what the likelihood is that we'll find one versus the other versus the other. So then, go ahead and answer this question with a numeric response. This is your question 16. Last question on that packet should be identically stated right here. I'd ask you to click in your answer first, and then you can talk to the person next to you and see if they agree. And then you can change your answer. But I want you to click your own answer first. I need about 10, 15 more clicks. Couple more. All right, I'm going to close out. Make sure your answer's clicked in. Oh, always get a few extras right there at the end. Can I see a hand raised? How many? What percentage? Percentage is awesome to do. Is it a high percentage or a low percentage? That's a terrible question to ask, isn't it? So we have a lot of people that are responding 0. Where did that number come from? It's not on your table, is it? Any new voices? New voices? New voices? Eric?
It would be listed as one of the percentages if any of them exist.
Okay, true. So on the table on the front, it does not show any of them that weigh 12.011 AMU. What's another reason, Christina?
It's the average of all of them, so not any one of them is going to be 12.0.
So remember the very first page, or the first part of Model 2 in your packet? It shows that some of these marbles weigh 5, some weigh 7. How many weighed 6.5? None of them, because that's the weighted average of them. It doesn't mean that anything actually weighs that much. So a couple days ago, I had a lot of students asking, well, shouldn't we use this number for talking about carbon? Well, if we're talking about carbon 12, no, we should absolutely not use that number. If we're talking about carbon 13, we shouldn't use that number. If we're talking about all the carbon that exists on this planet, then we should use that number because that talks about the weighted average. We're talking about a lot of atoms together. Okay, so all of the numbers on the periodic table actually have a lot more information hidden within them than you think. So chlorine was one of the ones that you worked with. 35.45. If I told you that all chlorines were either chlorine 35 or 37, what does the 35.45 tell us? Talk to your neighbor for a second. What does the 35.45 tell us? If we know it can either be 35 or 37. Can I hear from someone in the back row in this area here? Is anyone willing to volunteer? What does that number 35.45 tell us about chlorine? Josh.
You said 35 is one of the
Why does it have a higher percentage of chlorine 35 than 37 based on that number at the bottom of the periodic table? Great. The weighted average is closer to that one, so it tells us that there must be more of them present. There's a higher percentage of chlorine 35s, so it brings the average closer to that value. So that's a skill that we're going to be working on, is having you actually calculate the exact amount. So by the end of today's class, I want you, in our built-in study guide, to be able to utilize logic, like we just heard from Josh, right? Looking at the periodic table, saying, well, which one is more abundant, this one or this one, based on the weighted average. So just using logic to do that. But then also to compute the isotopic abundances from averages. And then we're going to start talking about nuclear decay. And I want you to be able to predict, like you did in your homework, your pre-class work, We're going to be talking about what types of nuclear decay there are and how we can predict which one might occur. And then that means you need to be able to identify what changes there are in the nuclear components, and that will allow you to figure out what actually happened. We're going to have to be able to predict which ones undergo nuclear decay as well. We're going to reference back to the belt of stability, which you guys will see is printed on the back of the worksheet I handed out today. For the most part, I'll try to bring a worksheet if we don't have a POGO activity. Something that helps you, instead of looking at the screen and writing down the question and spending a minute or two writing down the question will be there. So it allows you to engage quicker in thinking about the question as opposed to transcribing the question. It might be useful to get a 3-ring binder because there will be one of these almost every day in class. It'll help you keep them organized, and that will be part of a study guide. Sometimes I will remember to put the learning outcomes or learning objectives on the top of that page. Sometimes I won't. So I'll try to help where I can remember. And these are the terms we're going to be using. We've talked so far about electrons, protons, and neutrons. They are what they are, but it turns out that in nuclear processes, you can actually convert a proton to a neutron to a proton, and you can also kick out part of the nucleus. And so we'll be describing all 3 of those most likely today. These classes are so short. So not looking anything up, not doing any calculations. Go ahead and answer this first question. And this is not on your worksheet, I believe. No, it is. Number 1. I'm going to give you guys until that reaches 30 seconds to choose your answer. Okay, maybe I'll give you 40. 10 more seconds. Need a couple more seconds. We have bromine 79, bromine 81. This is the weighted average. Which one of these percentages is correct? 5 more seconds. And close it out. Okay, talk to your neighbor. How would you solve this problem? Without using your calculator. Put your phone down. Okay. Now you bring your calculator out.
That makes sense.
All right, can I hear from someone in the middle of the second to back row? How would we approach this problem? How do we choose from these without doing any calculations? No math. In this section here. There's some volunteers. Go ahead.
You can kind of like look at the average, it's 79.9, and then look at the 2 numbers that you're more closer to.
Okay, so what 2 numbers are you comparing the average? So the average is this one here.
79.90 and 79 and 81 is what we're looking at. It's a little closer to 79, but it's not like really closer to 79, so it's 1%.
Okay, so Josh, you want after that?
If you can just add what's in the middle of those 2 numbers? 80. What's it closer to? It's just basic looking at it right up front. What's it closer to?
Yeah, and so building, I think the combination of what you guys both said is fantastic. So thinking about where is this number compared to these 2, and what both of you basically are saying is it's really close to the middle, so I'm going to guess it's about 50-50. Then the question pushes you, because it doesn't give you 50-50 as one of the options, right? It gives you 49-51 or 51-49. So which isotope is there more of? 79 or 81?
79.
I heard both. So if it were closer to 81, we would see the average be slightly higher than the middle of the 2. The average is slightly lower than the middle of the two, so that means that there's slightly more of bromine 79. Okay, so that's how I want you thinking about this. If we're doing calculations, we're going to be doing calculations. Use logic first. Come up with a relative answer and say, well, there's going to be more of this one because it's closer to that. And then from there you can do your calculations, but always go back and check with your logic answer that you had. So this is a skill that we want you to develop in this class, is not using a calculator to come up with answers. So if we look at the periodic table, we're going to practice that again in calculations in a second. This is actually a really, really, really useful periodic table to use while you're studying. It's called the dynamic periodic table. Just Google it, it'll come up. You can click on any element, and so here silver is clicked on. You can see all the different isotopes of silver. So some elements have many more isotopes than others.
I think the highest is 10 with 10 isotopes.
So you can have a lot. And so some of them don't have many. And what we'll talk about at the end of class, and probably a little bit into next week, is how many of those isotopes are stable. Did anyone play with the PhET simulation, the atom builder PhET simulation? When you go into that, if you add protons, it'll change the elemental symbol. If you add neutrons, it'll shake. And what does the shaking mean? Unstable. And then when you get to a certain amount of neutrons to protons, it'll stop and it'll say stable. And then you'll add more neutrons and it'll become unstable again. And so we're going to be thinking about that ratio between protons and neutrons. Remember, those are all just different isotopes of the same element. And so here, this gives you a lot of information. So we can look at what type of nuclear decay they might undergo. And then there's different tabs you can select to give you different information about each one of those elements. So let's try to do this with calculations. So here's a problem. This is problem number 2. We're going to be talking about potassium. And I can't remember off the top of my head if there are more than 2 isotopes. But for the sake of this argument, let's say that there are 2 isotopes. Where did I find this number? The average mass. Bottom periodic table usually is 39.098. I'm going to simplify sig figs here for our calculations. So the first thing I want you to do is use logic. You can talk to your neighbor, go ahead and decide the first answer on there. Which isotope is found more frequently in nature? Which of those 2? Go ahead and click your response in, please. And then convince your neighbor that you knew that you have the right approach for getting there, or a correct approach, an appropriate approach. All right, almost everyone's clicked in. Woo! I'm going to put this on my fridge for the weekend. I feel like my kids did a really nice project at school today. So would anyone like to describe why? Why, looking at the information that we have here, would everyone, literally everyone in class, answer A? New voice, new voice, new voice, new voice. By the way, I don't see everyone's name tags. If you would be so kind as to bring your name tags every day until I learn everyone's names, which may be a while, that would be great. Fine.
We discussed that. We figured that because on the periodic table, it rounds to 39.1, that there would be more of those in nature as opposed to.
Okay, can you elaborate on that a little bit?
So the atomic mass of the periodic table, it says it's like 39.
Yeah, the average atomic mass.
It would be 39. So when we were looking at the one found most frequently in nature, we figured it would be potassium 39 because it's more of those.
Okay, so I'd be a little bit careful with saying that the average rounds to 39. We're not necessarily rounding, and maybe that was my fault because I rounded the average mass here. And you'll see in a second why I did that for our calculation's sake. So let's build on that. I think there's definitely some good logic in there. Let's build on that as well. Eric?
Not that we need it, but it is up there. When it says name, mass, and abundance,
Okay,
it says 93%.
great. Another resource. resource that you had. Sure, awesome. What else? Let's think about the logic behind it. So the logic, can we build off what Marlene, is it Marlene? What she said, sorry, the E is a little curly Q at the end, I wasn't sure if it was an A or... yeah, Kyle.
So the mass, 39, the average mass of 39.1 is much closer to 39 than it is to 41.
Fantastic. All right, that's exactly what I wanted to hear. Is this idea that we're looking at what it can be, what the two bookends are, and then saying, well, where is it in that span? It's not just about it being close to 1, it's about being closer to 1 than the other. Okay? So it's that relative to something else. And so not only is it closer to 39, it's a lot closer to 39. So now go ahead and do part B. And I want you to calculate what that percentage is. You may or may not know how to do this, so you're probably going to have to turn and work with people around you to figure out how would we show mathematically what percentage we have of each of the two. And I want you to calculate both of them, but I'm going to have you click in the percentage of potassium 39. Enter it as a percentage. And let's just do, report your answer as 3 sig figs, just because it'll be easier for me to see in the clickers. So for this calculation, you can assume potassium 39 is 39 AMU, potassium 41 is 41 AMU, and the average is 39.1. Is that okay? There's more accurate versions of those numbers, but for the sake of how we're doing the calculations today, we can just say 39 and 41 are the masses. Good question, Carl.
That's what I did in the simulation. I just know how to get from the bottom to the bottom, so I'm just doing how they did it. So I know
You understand what she's doing? Yeah. All right, I wanted you guys to get a minute to try, kind of set things up on your own, see what you do know and what you don't know. So let's talk through this problem. And hopefully by discussing it, we can kind of all get on the same page as far as one logical approach. There's a few different approaches to how you can answer this type of question. So the approach that I'm going to talk based on, or describe here, is that if we only have two possible isotopes, what's the relationship between the percentage of one and the percentage of the other? How do those two percentages relate to each other, Amber?
One percentage you can find by subtracting the other from one.
So don't talk about the approach yet. Well, maybe you're getting to the right point. Sorry. Or the point I was trying to get at, not the right point.
You can subtract one, find the other. If you subtract one percentage from one, you can find the other percentage.
Okay, and another way to say that is they both add up to 100%. Right? So if they both add up to 100%, take 100% minus 1 and gives you the other. Yeah, so saying forwards, backwards, same thing. Sorry, I thought you were starting to talk about the solving this question approach and not the relationship, but nicely said. Okay, so if the two percentages add up to 100%, so for chlorine, 75% is 1, how much of the other do we have? 25%, right? Those two percentages add up. And we're going to be using decimal format, so instead of 100%, we talked about this the other day a little bit. So a total of 1 would be the sum of the percentages, 0.25 plus 0.75 gives 1. So the other way to say that is exactly like Amber said. If you take 1 minus the percentage of one of them, that leaves you with the percentage of the other. So let's use that to set up an equation that looks at our two percentages. Can you see the gray? Sorry, it's not. I didn't realize that was so light in color. So maybe discuss this equation with your neighbors. What is this equation doing? Why is this equation helping us set up that relationship? Talk to the person next to you. See if you can discuss why this equation. So 3 sig figs as a Did anyone here in their group a good explanation for kind of what this equation allows us to do with the information that we have so far that they want to share with the class? Matthew?
Well, if X is going to equal one of the percentages for one of the isotopes, then 1 minus the same variable is going to be the percentage for the other isotope.
Okay. So then how does that relate to this equation?
Because the calculation of those two will always equal the average mass.
Okay, where have we seen this equation before? Where have we seen them set up in this format? Love? Great. On the front page of this packet, approach 2, to find the weighted average, if we know the percentages, remember that's what it was doing the other way around from what we're doing now. So it's saying the mass of one times the percentage plus the mass of the second one times its percentage gives us the weighted average. The thing is, we didn't know the percentages here, but we know how the two percentages relate. We know that one of them must be related to the second one through this relationship that we just described. So then go ahead and do your calculations. Try to figure out, making sure to answer the percentage. And I want, not decimal, I want you to convert it back to percentage using 3 sig figs. Go ahead and click in your answer for what is the percentage of potassium-39, and then how does that relate to the percentage of potassium-41? You're not going to click in that second part. Because what? Okay, that's fine.
Oh, okay.
News to me. Is that kind of, that's the approach you guys used, right?
Yes.
So then what did you end up finding?
It's going to be 0.95.
I appreciate you putting the 0 there.
And then this is going to be back to 95.0%.
Great. And what is that?
That's the abundance for 39.
Great. And so what is it for 41?
It's going to be 5%.
Raise your hand if you would like some guidance. Caleb, do you need this one?
Yeah, in a second. See the shit through them first.
Okay. Caleb, would you mind discussing your thoughts with Eric as well?
We need to add the percentage.
What do you mean?
I have to get this into the equation. I have to get X over to here.
Oh, you're just thinking of order of operations?
No. Well, sure.
Okay, so
That's a great way to word it.
So this is going to be like way back in history, right? So you have
16
39.0x
Okay.
plus, and then how does this work out mathematically?
Well, this is going to be multiplied by the percentage.
So what are you going to get for these multiplications?
you multiply right here.
Okay, so you multiply this times the first one, multiply it times the second one, you get rid of the parentheses. So 41 times 1, 1.
Right.
41 times negative x.
Negative 41x?
Yep. So rewrite this equation, but with that simplified, and then figure out how to isolate x.
So you wanted a decimal
Percent.
I see how I got that.
Can I see a hand raised back here as well? Young?
I don't know yet. We'll see.
the right.
Okay, so think about what that would mean for a percentage, and make sure you fully understand that approach and how that relates to the second isotope as well. Okay, so I only have 39 clicks. Does that mean that people are still working on this?
Yes.
So we're only going to take about 1 more minute on it. So if you still have questions, please raise your hand. I'll come around, or Sam will come around and help you with this. Questions? Questions?
I just wanted to know, when you said calculated to 3 sig figs, do you want us to put like a 0 after the percentage, or like, because it's coming at
That seems appropriate.
right?
Yeah, that would be 3 sig figs, right? Will the clicker let you do that? I know, that's what I was joking, saying does it let you, and turns out the answer is no. So this is an approach that I will admit was not intuitive to me until I saw it done, and then I realized what the math was letting me do with the relationship between the two percentages. What happens if we have 3 isotopes?
It's harder to calculate, but as long as you still have one variable, you can use the mathematical equation to calculate the abundance of each isotope.
Yeah, if we have one equation, how many unknowns can we solve though?
1.
So here,
You need 2 equations.
we would have to have 2 equations, or we would have to only have 1 unknown percentage.
Yeah.
So it gets a lot muddier once we get more than 2 isotopes. And for this class, mathematically, I'm not expecting you to solve for more than 2 isotopes. Okay, so if you have, what you're expected to do in this class is if you have the 2 percentages, you should be able to find the weighted average. If you have the weighted average, you should be able to find the 2 percentages. That's what I expect you to be able to do, back and forth in both directions. And to do that with logic first and check, and then also to do that with calculations. So let's see what our clickers tell us here for our answer. It looks like 80% of the class said 95, and then we have some others that are in the same range. So these ones are a little bit distinct from it, so I'll go through the rest of my calculations, and then we'll try to think about how those arose. So first we have to take the 41, multiply it by both things in the parentheses to make sure that we don't have parentheses and we just have x's and numbers. Once we do that, hopefully we got to something similar to this, where we have 2 different sets with x's and then 2 numbers without any x's. Once we simplify that all down, we get negative 2x equals negative 1.9. And then we can solve for x, and I got 0.95. And then we have to convert that back to a percentage based on what I requested. And so 0.95 is 95%. How did I come up with 5% for potassium-41 then? Can I have a hand raised? I heard a lot of voices. Matt, was that you?
Yeah, you just take 1 minus 0.95.
Great. Or if we're doing percentages and we'd already converted it, we'd do 100 minus 95. Or if we did decimal, 1 minus 0.95. Because we know there's only 2 isotopes, they have to add up to 100. That's why this whole set of equations was used. So that means that we can solve for the other. The one thing that I see students get stuck on a lot in this type of problem is that you forget what you define to be x. If we did all of these calculations, but we had this one be x, and this one be 1 minus x, would the answer be the same?
No.
If we had switched x from here, and this would be 1 minus x, what would that do differently to our results? Hand raise, please. Dawson.
It would find the mass for potassium 41.
More specifically, it would find what? We would be calculating what?
The mass average of potassium 41.
Not the average. Moab?
See, I actually did that the first time around, and basically I got a percentage over 100, which is weird.
So, I'm not sure how you would get a percentage over 100. Yeah, Aaron?
It would just calculate the percent abundance for potassium 41.
Great. Okay, so building off what you said, a little bit tweaked. If we had this as our x, then we'd be calculating the percentage of potassium 41. It would be not the average, it would be the specific percent abundance for that isotope. All right, so we just need to be really careful to find what did we say is x, what is 1 minus x, and then see how those two things relate to each other. Okay, any questions on this approach? You will have chances to practice this on your homework, I believe. Yes? I'm looking at Natalie. Okay. If not, I'll make sure to get you guys some practice problems. Email me or post it to the campus discussions if we don't have practice problems. This is something you need to practice for sure to get the hang of. Yes? The answer.
And we're always going to assume that it's just like 39.0.
So if you had a table in front of you that said the mass of potassium 39 is 39.0726 whatever, you would use that. You would use the more accurate numbers. For this particular example, I simplified everything so that we could just look at the process instead of the more technical numbers. If you were to go on a test and just be lazy and use 39 for potassium 39, but you had that extra information, it would be most likely a short answer, and I would dock you a little bit of points, but you wouldn't get the whole question wrong. So there was a question actually in the reciprocal interview, what do my tests look like? Our final exam I mentioned the other day is going to be, the ACS final is one of the options, which is all multiple choice. My test that I'll be giving for midterms will be half multiple choice and half short answer. There will be partial credit on the short answer. There will, unless I can figure out a brilliant way, there will be no partial credit on the multiple choice. And multiple choice questions actually can be harder than short answer because how we come up with the other answers besides the right one are what are common mistakes that students make, and that's the answer that you put there. So if you see an answer that you agree with, that doesn't mean that's the right answer. Make sure to check your work always, because multiple choice can be very challenging for that reason. Say again? The regular exams, the 3 midterms are half and half. The final exam, one of the final exam options is all multiple choice, which is the American Chemical Society. I'm going to try to figure out logistically if I can give you an option to take a second final exam. The highest of the 2 scores would be your what you get for that. All right, so now we're going to shift gears and start talking about nuclear chemistry. So we've been talking about all these different elements and how they have isotopes, and I like to do this in the beginning of the semester because I don't like students to get this mindset that if it is polonium, it will always be polonium. There's no way it can change from polonium. There are examples where those elements are changed from one element into the other. They are not super common. They were not fully described scientifically until the late 1800s when Marie and Pierre Curie worked on radioactivity and tried to categorize what it was and then study it. There's some fascinating stories about Marie Curie if you guys want to go and spend some time reading about it. An amazing woman that had 2 Nobel Prizes to her name. She died by the time she was like 52, I think, or something like that. So, ridiculous, right? So she was one of the ones responsible for actually figuring out what radioactivity was and then utilizing it. And so the things that we use radioactivity for now are we use it for radiocarbon dating to see how old things are. The original people who described and categorized what an atom was composed of, they used that radioactivity. It was only about 10 or 15 years after Marie Curie had discovered radioactivity. They used it to kind of probe what an atom was. We'll talk about that in a second. There's a lot of different things we can look at the age of. I'm not sure why those came out at different times. And then we can use radioactivity in medicine. And there's a lot of different places that radioactivity is used. So The example here is PET scanners. We can use that to study tumors in the brain by attaching something that emits radioactivity onto sugar, and then our brain takes that up in this instance. Tumors will take up more of it than a non-tumor, or certain parts of a Parkinson's brain. You'll see more of it absorbed in certain areas, and so you'll see more radioactivity coming out from a certain part of the brain. This is actually some of the work that I did before I went to graduate school, was trying to develop radioactive tracers to see diseases to a greater extent. So if you ever want to have a conversation about this stuff and what it looks like in medicine, that's something that's very interesting to me. So let's take a look at a type of radioactivity called alpha decay. Hopefully you guys got a chance to read a little bit of this in your textbook, chapter 25, and saw some on pre-quiz. So this is uranium decomposing to thorium. So this isotope of uranium-238 is unstable. It would be hard to build in that atom builder. Why would this be difficult to build in that atom builder app website that I had you guys working in? It's a lot of one by one of. How many protons does this uranium have?
92.
92. What about the other uraniums? 92. Okay.
Oh.
What's different about different uranium isotopes?
Neutrons.
And hence the mass number. Okay, just going back to what we talked about the other day. So this uranium atom is unstable, it decomposes, and it emits an alpha particle. Let's go ahead and click in. If that alpha particle were to be described as an element, what element would it be? You can talk to your neighbor too if you're not quite sure. Let's do a symbol. Symbol instead of the name.
Did you just want the symbol?
Oh, so put it here. Oh.
Where are we at on this thing? A couple more seconds. Go ahead and click in the symbol for the element that that alpha particle could be described as. All right, closing out. We have three options. One has a vast majority. Why would we describe that alpha particle, could we describe that alpha particle as helium? Yeah, Bria?
Because if you look at the bottom number, it has protons and helium.
Great. So any nucleus with 2 protons is going to be helium. How many neutrons does that particle have? 2, because this is the sum of the number of protons plus neutrons. So is this helium? Exactly. So I'll tell you that this one is a little bit tricky because we're actually not showing any symbol up here, but an alpha particle doesn't have any electrons. And so an alpha particle is the emission, the spontaneous emission of 2 protons and 2 neutrons from the nucleus. So that basically takes the nucleus that's unstable, and then by losing 2 protons and 2 neutrons, moves it into a state that is more stable. Mode?
So the alpha particles always have 2 neutrons and 2 protons?
That is the definition of an alpha particle, absolutely. Yes?
Would that make the thorium -2 if it kept the electrons?
Seems logical. Let me look into this after class. Very good question. Yes. I need to... Scatum. An alpha particle has no electrons, so if we emit that from a nucleus, it would leave behind 2 more electrons than protons. Thoughts? Yeah, let me think about it. Very good question. So I will come back to that in class, or post some into Kim's discussions maybe about that, but very good question. So these particles were some of the particles discovered in the late 1800s. And so 3 scientists, Rutherford, Geiger, and Martson, which were professors and graduate students, I believe, actually used these to study the nucleus itself.
They discovered helium because the way they were able to discover helium, because it's floats out of the atmosphere, is that they actually studied alpha emitting stuff, and they found helium off that.
And they were able to trap that and study it?
Mm-hmm.
Awesome. So we're going to look at the original experiment that these guys did studying the nucleus. So at the time, in the early 1900s, they thought that an atom, they realized that it was composed of some positive stuff and some negative stuff. They didn't quite know exactly what. And they knew that those were quantized, that you could have individual components that were positive and components that were negative, but they didn't know what they looked like. And so they proposed this model of the atom that they called the plum pudding model. It's much more relevant in Britain, I think, where plum pudding is a thing that people eat. But plum pudding is basically this mush, and it has raisins, I believe, in it. Or I guess you could put plums, but they'd be really big. So they have little raisins kind of dotted throughout it. And so their proposed model of the atom was that you had this whole space of the atom was kind of this positive area, and then you had little negative charges. And part of the reason they thought this was true is because they knew they could remove 1 electron at a time, but they hadn't seen the ability to remove 1 proton at a time. So they thought the positiveness was just a big, vast kind of area of positiveness. So the way that they tested this was they got a small film of gold, pressed it extremely thin, so like a piece of paper that was made out of gold, really small, very expensive. And it was so thin that it was only a few atoms thick. And what they did is they fired these alpha particles perpendicular to it, and they fired these alpha particles to see what would happen. And their prediction was what's drawn here, and that they would have these particles shoot right through, and because the positiveness was kind of dispersed throughout, most of it would go through. Every once in a while it interact with an electron, and it might be kind of pulled a little bit off center. So what do you guys think would happen? Knowing what you know about the atom, what do you think would actually happen? I believe this is question 4?
6.
6.
Can you make it multiple choice?
Is it not multiple choice?
It's not.
You should be able to zoom in on the screen if you can't see the answers. Once you've read the question, you can discuss with the person next to you. Science has a tendency to forget. See that? So based off of their proposed plum pudding model, which one of these answers do you think would have been most likely? That's not the question I asked you guys. So A kind of describes a small fraction of them were deflected or kind of turned a little bit. So let's see what you guys... So we have some answers all over the place. So what's different about the model of the atom as we now know it versus what they thought?
There's the nucleus, which is such a densely packed charge.
And what kind of charge is it? Yeah.
Because what would have happened?
Pause right there, and let's look at some models of what would happen. Okay, so the difference is we now know that the nucleus has a very dense positive charge. It's not diffuse like this. And so when they actually did the study, they shot the alpha particles from here. They expected them mostly to go through the foil, and for most of them just to be deflected a little bit. But what they saw that they didn't expect was that a number of alpha particles were actually coming back towards the detector. Why? Kayla? So this is true, but that doesn't actually describe why most of it went through.
Because atoms are mostly shapes.
Raising. Kevin, I see you raising your hand.
I was thinking that aren't all metals positively charged? No.
Ruby? They can be.
Would the alpha particles interact with the nucleus and then go back because they're the same charge as the nucleus?
So if we look at what the nucleus and the atom actually looks like, there's this dense core of positively charged particles in the center, called the nucleus, but then everything else is kind of negatively charged where the electrons are. So every once in a while, one of the alpha particles would actually collide with the nucleus, and here's a kind of cute little animation, that they might be deflected a little bit if they came super close, but every once in a while, you would get an alpha particle that would actually bounce off, positive charge, it would bounce off and come back. So this is how they ended up figuring out that the nucleus actually is part of the atom, that the positive charge is not diffuse like the plum pudding model, but there's a point source in the center of each atom that has a positive charge. So let me just briefly go back to this. On the back side of your worksheet, you have the belt of stability. And I think this was in one of your problems for pre-class. Just to make sure we're all oriented in the same place, the bottom axis, this is the number of protons. Y-axis is the number of neutrons. So if we have carbon 12, we would look on this and see where does it fall. We have 6 protons, 6 neutrons, so it's one of these dots that's right here. Carbon 13, does that fall above or below carbon 12?
Above.
There's one more neutron, so it would be the black dot right above. Carbon 10 is below. And so if we go out and we look in nature, this is really an example of describing what we find in nature. We find all these black dots are isotopes that exist in nature and are stable. And then these gray ones are all isotopes that exist that are not stable. So the big question in predicting radioactive decay is if we had an isotope that's up here, what process would it undergo in order to move closer to the belt of stability? So how would we convert a neutron to a proton, protons to neutrons? There's a lot of different things that can happen. We'll have to pick this up again on class on Wednesday. So go ahead and come up with questions. I hope you guys have a good weekend. There is a homework. I may move it to be due Wednesday night because there's some nuclear on it. Let me take a look at that. I'll send an announcement with that.